Okay, so here we're going to practice creating confidence intervals for a single proportion, as well as review some older topics like binomial distributions, sampling methods, even distribution shapes. Number one, changing from a 95% confidence interval estimate for a population proportion to a 99% confidence interval estimate with all other things being equal. What does it do to the interval size? So you might be tempted to say, well, you have to know the sample size. Actually, you don't. So first of all, let's go ahead and look how we calculate margin of error, because that's what determines how wide our interval is. And it is z star times the standard error. Now, 95% tells you that z star is 1.96. You should be memorizing that. And 99% though is not as simple. It's on the calculator. You basically do inverse norm, 0.99, then your mean is 0, your standard deviation is 1, and you want the center. So I will be showing you how to do that on the calculator on another problem. So you get a z-score of negative 2.576 to positive 2.576. So the margin of error for the first one is 1.96 times the standard deviation, or standard error really, and margin of error for the second one is 2.57 times the standard deviation. So the factor, when I divide one by the other, my new interval being 99%, is the one you put on top. You can see it is 1.314 or 131%. So the increase is 31%, so it increases the interval size by 31%. Number two, a survey was conducted to determine the percentage of high school students who plan to go to college. The results were stated as 82% with a margin of error of plus or minus 5%. What is meant by plus or minus 5%? So looking at your notes for this unit, for this particular chapter, it's like on the top of the second page, it says, what is a confidence interval? It is a range of plausible values for the parameter based on the point estimate. The point estimate is the midpoint of the interval. The distance from the point estimate to the edge of the intervals is called the margin of error. You can also calculate it by dividing the width of the interval by 2. All right, so the plus or minus, or this interval right here, tells us that we can go 5% this way and 5% that way, and all of these values are plausible, all right? If you're outside, these values are not plausible. So it has nothing to do with the number of the percent of population surveyed. Now you might be tempted to say, oh, in the sample, the percentage of students who plan to go to college was between 77% and 87%. But the problem with that answer is we know the sample actually was exactly 82%, and we're trying to estimate the population. And then in C, the percentage of the entire population of students who plan to go to college is between 77% and 87%. You can see how certain it is. It says is, and this is just our confidence interval. For us, this is a range of plausible values, all right? It's possible it could be something else, but we're not 100% sure. So D, it is unlikely that the given sample proportion result would be obtained unless the true percentage were 77 and 87%. So these are plausible, probable things out here, unlikely, all right? And it has nothing to do with the percent of population surveyed, so your answer is D. Number 3, in the random sample of 1,250 adult drivers, 450 said they would cut their driving by 10% if this significantly helped the environment. Find a 95% confidence interval estimate of the proportion of adult drivers who are willing to cut their driving by 10% to help the environment. So again, remember the structure of a confidence interval. Just like we looked in that first slide you saw, it's your point estimate plus or minus your your margin of error. And your margin of error is your critical value times your standard error, the statistic. So your statistic is 450 divided by 1250, which is 0.36. And that kind of makes sense. They all have the 0.36 Z star is 1.96. So you memorize this for a 95% confidence level, all right? And these all have 1.96. So we haven't really eliminated any possibilities. You can see it is different on the standard error calculation. And basically for standard error, you take your sample value, p hat, which in this case is 0.36, and you substitute it in and you put in your sample size, and that happens to match D. D is the correct answer. Number 4, in a survey funded by Burroughs Wellcome, 750 of 1,000 adult Americans said they didn't believe they could come down with a sexually transmitted disease. Construct a 95% confidence interval, the proportion of adult Americans who don't believe they can contract an STD. Now, again, if this was free response, we would be checking conditions. Survey, we're going to assume that you'd have to assume that they randomly sampled this. They didn't say. Then also, we look at the number of successes and failures. You have 750 successes, 250 failures, so that's fine. And then we know 1,000 adult Americans, that's less than 10% of the whole population. So don't forget to quickly check conditions, especially for a free response problem. Here, I mean, we know we're in the right area because they're saying construct a 95% confidence interval. So here's the information I need to do that. And so I have n equals 100, x equals 750, confidence level is 95%. So that tells you that my Z star is 1.96, all right? So we know the Z star, but we're missing the standard error. So we have this formula for calculating it. And then you basically go 0.75 times 0.25 over 1,000. So 0.75, that's the 750 out of 1,000. And 1 minus that over 1,000, and you get, I left off a decimal, I'm pretty sure. Oh, there's my p hat. I went in wrong order. 0.01. So there should be a little point right there. Sorry about that. Equals 0.027. And so we say, oh, the interval is 75 plus or minus 0.027, which is 0.77. And so your answer is B. Now I'm also going to show you how to use the calculator to get this value. So to do a confidence interval quickly, you're going to go stat test. I know you're like, it's not a test. It actually is. It's a one prop. It's really called a Z interval. All right. Actually, we probably make sure there it is. A one proportion Z interval. So you can hit enter. And the way this one works is that you actually have to have a number of successes. So on this Burroughs Wellcome, they told us there are 750 successes out of 1,000. And then you hit calculate. That's the right confidence level, 95%. Hit enter. Voila, there you are. Number 5. A politician wants to know what percentage of voters support her position on the issue of forced busing for integration. What size voter sample should be obtained to determine with 90% confidence the support level to within 4%? So when you're trying to determine sample size, that is the most difficult thing we do in this unit when we're dealing with confidence intervals. First of all, we need to know the margin of error, which is 0.04. Remember, 4% becomes 0.04, not 0.4, so make sure you get that right. The confidence level is 90%, and we want to know what is n. So the first thing we need to do is find the critical value, which is Z star equals, we're going to do inverse norm, where we have set the confidence level at 0.9, the mean at 0, standard deviation of 1, and the center is the center area we want. So let's show you how to do that on the calculator. Okay, to find a critical value given a confidence level, you have to hit second distribution and go to number 3, inverse norm. So this is assuming, again, that you are using the normal distribution, which is all I've taught you so far. So we're doing a 90% confidence level. You need to do that as a decimal value. If you want to put 0.90, that's fine. And we're doing a Z value. So that means we're using the standardized distribution where the mean is 0 and the standard deviation is 1. And since we're doing a confidence interval, we want it centered around our point estimate. We don't want the left side or the right side, but the middle. And then hit enter and scroll down, hit enter, and then voila, there you go, negative 1.645 roughly to positive 1.645. So now that we have that, we can start plugging into the margin of error formula where Z star and S of E. But you're like, but you already know the margin of error. That's correct. But we can determine sample size by substituting in the formula for standard error. So we have this formula, which you're going to write pretty frequently, really. And it comes from this piece right here. And we don't know p hat. So it's like, wait a second. What's p hat? So we have to assume the worst case scenario. In your notes, I went through an example. If you don't know p hat, 0.5 does give you the worst case scenario. You can look at it and see that that's the maximum margin of error. So we want to make sure that we're not underestimating the margin of error. We want the margin of error to be good and that our sample size gives us at least as tight as that. Okay. So we substitute in the 0.5 and the 0.5 because 1 minus 0.5 is 0.5. And let me go ahead and get my pointer. And you can see the left side is the 0.04, and there's a critical value we found. So you're going to want to keep it, the 0.5 is going to come out of the square root because 0.5 squared, take the square root, is just 0.5. So we just have the square root of our sample size here. Let me go ahead and multiply these two out. And that makes it a little bit easier. And if you rewrite the equation, you can multiply both sides by square root of n, right? So you end up with 0.04 times square root of n equals 0.8225. So those of you who like algebra, here you go. Enjoy. Divide both sides by 0.04 and square both sides. Now, the next piece here, if I had given you the option of 422 as an answer, if this had been 0.168 instead of 0.816, it's still 423. You want to go at, even if this was 422.0, you want to round your answer up to the next one because it was, you want to make sure you have enough. You don't want to be too small. So this always goes up one digit and we get 423 as our answer. Number 6, in a study of Parkinson's disease, 100 volunteers had incisions made through their skulls. The patients were randomly sorted into 2 groups, one of which had a new drug inserted into the brain. Yikes. In the other group, the skulls were closed with no treatment given. The patients did not know who received the drug. Sounds a lot like that episode of Grey's Anatomy. Anyways, in the weeks to follow, all 100 volunteers showed similar improvement in physical condition. What is this an example of? So again, if you saw that Grey's Anatomy episode, they were doing treatments. I'm pretty sure it was for Parkinson's or Alzheimer's. I couldn't remember which one. And they were doing surgeries for everybody, those who got the treatment and those who didn't. So this is very much like that. So everyone who got the surgery felt treated, right? All volunteers showed improvement. They probably feel better because they're being attended to. And why is that? It's called the placebo effect. Number 7, which of the following statements is true? 2 students working with the same set of data may come up with different histograms. So we're dealing with a set of data and looking at histograms primarily, right? And sometimes stem plots. So probably the easier thing for me to do is to go ahead and use Statlet to look at what happens when we create histograms. So I'm going to show you why choice A could be true, is true. All right, so I put a bunch of the data in. Here's the dot plot of Unit D exam grades. I just went to one of my old tests and gathered all the data. And you can see, first of all, they asked, would it come up a histogram? So first of all, let me go ahead and scroll that. There's my histogram. And you can see you can change your interval widths. You can change your interval widths. So now the histogram looks slightly different than when I had 10 as the width. And I can also change boundary values. If I put a 5 as a boundary value, the histogram changed. I could do that. And I could change it to so it's like something weird, like 7. So the histogram you can change a lot, okay? It says displaying outliers is less problematic using histograms instead of stem plots. Well, first of all, if I do a stem plot, okay, I can see it's possible I have outliers. It's easier to see the individual data points. I can see if I have gaps. Let me go ahead and do a box plot so we can see if, yeah, we do have one outlier at 12, all right? So I'll go back to my stem plot, and you can see there's a 12, and it's a little bit harder to see, but with a histogram, it's definitely harder to see. You don't know that that's an outlier right there, okay? So again, part B is not as useful either. Histograms are more widely used than stem plots or dot plots because histograms display the value of individual observations. As you can see, the observations are grouped together. They're not individual. Stem plots do a good job of showing individual data. Dot plots show a good job of showing individual data. Unlike other graphs, histograms do not, axes do not need to be labeled. Of course they need to be labeled. And if you look, if I create a histogram, there are labels. We have frequency and then the grades. A histogram of a categorical variable can pinpoint clusters and gaps. We are in quantitative. Histograms are for quantitative variables, not categorical variables. So the true statement is A. Number 8, suppose the average outstanding loan for college graduates is $23,500 with a standard deviation of 7,200. In an SRS of 50 graduating college students, what is the probability that their mean outstanding loan is under $21,000? So we have the mean for our population, all right? It's 23,500. Notice I'm using the mu symbol and it's X, and the mean for the individuals. And standard deviation for individuals is 7,200. And then the probability that my sample statistic, X bar, is less than 21,000 is what? So first of all, the mean for my sample statistic should be the same as the mean for my population, but the standard deviation for my sample statistic should be smaller, all right, because we got to divide by the square root of the sample size, and now it's $1,018.23. So basically what we're going to do is we're going to do normal CDF with a lower of negative infinity, upper of 2100, a mean of 23,500, and an SD of 1018. And if you plug that all in the calculator, you get 0.0070, which is this answer, but I'll also go ahead and show you how to add that in on the calculator. Okay, to find probability using normal distribution, second distribution, we're going to normal CDF. And we said the lower, actually we wanted, it is under 21,000, so we already have the correct lower in there. And then my upper value is 21,000. There we go. My mean is 23,500. And my SD is 1018. Now I could have done this all with Z-scores and not had to change the mean, but it's a little bit more work to actually go calculate the Z-score. It's not bad. And then calculate, and we get the 0.0070. Number 9, a coin is weighted so that the probability of heads is 0.75. The coin is tossed 10 times, and the number of heads is noted. This procedure is repeated a total of 50 times, and the number of heads is recorded each time. What kind of distribution is simulated? So we're counting the number of heads, so it's binomial and not a proportion or a mean. The coin is tossed 10 times, all right? So N is 10. P is given as 0.75. Now you might have been tempted to say, wait a second, there's a 50 up there. That means there are 50 simulations, all right? So it didn't say, oh, there are 50 simulations and how many times did heads come up in the total number of simulations. They just said we're doing this 50 times and reporting the number of heads. So from a trial of 10 times. So your correct answer is N is 10 and P equals 0.75. Number 10, the graph below shows a cumulative proportion plotted against age for a population. The median is approximately what age? Well, the median is the 50th percentile on a cumulative distribution function. So I'm going to go here from the 50th percentile. Remember, here's the percentages here. It starts at 0 and it goes to 1. So instead of going like this, I know you normally want to go on X. But these are the ages, and you're trying to figure that out. So you don't know that. But you do know the fraction, which is 50%. So you go till you get to that point, drop straight down, and the number closest to this is 17. Number 11. Consider the following 3 scatter plots. What is the relationship among R1, R2, and R3? The correlations associated with the first, second, and third scatter plots, respectively. So for the first one, R1 is between -1 and 0. Not quite all the way to -1. I'd say probably maybe a negative. It might be a moderate to a strong fit. For the second one, it's pretty much 0. There is no relationship, okay? And then the last one, oh, this looks like a perfect fit. It must be very close to -1 if it's not exactly -1. So R3 is the most negative, followed by R1 and then R2. 12. There are 2 games involving flipping a fair coin. In the first game, you win a prize if you can throw between 45 and 55% heads. In the second game, you win if you can throw more than 80% heads. For each game, would you rather flip the coin 30 times or 300 times? So let's look at what coin flips look like for 30 times. So for 30 times, you can see right in this area would be 45 to 55%. So if I calculate the probability there, you have a 42% chance of winning the first game by playing it with 30 flips. And you have it's not very big, 0.07% probability of getting 80% or more hits on the right, okay? Then let's go ahead and look at the next distribution for 300 times. So for this probability of playing the first game, it's like a 92%, 93% chance of winning. But the probability you'll win the second game is 0, so almost 0. So you thought, oh, that was small, this is even smaller. So you don't want to play the second game with 300 flips, you'd rather play it with 30. And you'd rather play the first game where you want to be in the center with 300 flips. Number 13. Consider the following parallel box plots indicating the starting salaries in thousands of dollars for blue-collar and white-collar workers at a particular production plant. Which of the following is a correct conclusion? So here they're talking about ranges. So one important thing to keep in mind, you can't tell means. So B, I don't know. You can't tell symmetry, and you can't tell shape from box plots. So B, C, and D are out. And distributions are not outliers of each other. And therefore, we left with choice A, which is that the ranges are the same, and they do look the same. So the answer is choice A. And our last problem, a simple random sample is defined by, you have the method of selection, examination of the outcome, both of these, or how representative the sample is of the population. You can't tell if a simple random sample is taken by looking at the outcomes. So it's not B, I can tell you that right now. And other methods can get representative outcomes. Sometimes they're actually better, like if you do stratified, right? You can make sure you get representation from each group. So really, you know it's a simple random sample by how you took it. And the one other thing that's useful to know is that if you can get the same, each group of the same sample size has the same probability, that's another thing about knowing that it's a simple random sample. That's a characteristic of it. But the best way to know that you took one is to know how they took it.